and this example probably popped up in most textbooks. We want to find the dimensions of the largest rectangular box by volume that meets a certain condition, and that condition is that such that what is it, the length plus the girth, yeah, such that the length plus the girth is less than or equal to 108 inches. Okay. So let's call the length this dimension, and the girth is the around dimension. So we want the length z plus the girth, which is going to be x plus y plus x plus y. We want that to be less than or equal to 108 inches. Okay. So the way we're going to do this, well, we're going to do it two different ways. First, we're going to do it the typical way. Then we will do it the kind of the LaGrange multipliers way. So if you want something to be, if we want the maximum volume and we have this constraint, we're clearly going to set this equal to 108 so that we get the biggest box possible. So we're going to set, and again, right, we're going to try and write things as a function of two variables. We're probably going to end up solving for z. So I've got z plus 2x plus 2y. Why am I writing it again? Let's say it's equal to 108. And we also want to maximize the volume, which is equal to x times y times z. So if we're doing this the way we were doing it last time, we want to write volume as a function of two variables. So we're going to use this constraint to isolate one of the variables, typically z. So we're going to isolate z. We're going to say z is 108 minus 2x minus 1. And then we are going to plug that in here. So we've got the volume as a function of x and y is equal to x times y times z, which is 108 minus 2x minus 2y. So for those of you that just popped in, we're just doing this problem. We are trying to maximize the volume of a box that we can mail, and the mailing requirements are that the length plus the girth, so z plus x plus y plus x plus y, is less than or equal to 108 inches. And so then we've written our volume, x times y times z, as a function of two variables, x times y times 108 minus 2x minus 2y. And I would probably multiply this out. So I would write this out as 108xy minus 2x squared y minus 2xy squared. And now we're going to find the critical points. So we're going to take our partials. Our partial with respect to x is 108y minus, let's see what we're going to get here. We're going to get 2x squared minus 2y squared. Sorry, that's not right. 4xy, apologies. Partial with respect to x, not y. 4xy minus 2y squared. And then our partial with respect to x is going to be 108. Sorry, our partial with respect to y. Jeez, come on. 108x minus 2x squared minus 4xy. There is something worth noting here, I think anyway. If you look at this function as a function of x and y, I would say that this function is symmetric in x and y, meaning that if you interchange x and y, right, if you replace y with x and x with y, you still get the same equation. And if you change all the x's to y's, you get 108yx minus 2y squared x minus 2yx squared. That's the same equation as it was before. What that typically means is that when you find critical points, usually the x and y values are the same. That's just something I've noticed over the years. There's probably some justification for it, but it's nice to see that if you've got a function where like if you interchange x and y, you get the same function, it usually means your critical points have the same values. So we want to find our critical points. Okay, so solving this equal to 0 looks like it might be hard, but I can see I can factor out a variable from each of them. From this first one, I can factor out an x. So I'm going 100x times 108 minus 2x minus 4y. So that's going to, and I probably need, oh, that's fine. We'll go to the other side of the board. So I've got, my Vx was, sorry, it was 108y minus 4xy. Minus 2y squared. And then factoring out the y from that. So let's just factor out the y. Smart. We just wrote down the Vx one was. I know it's going to be the same as this, except with x instead of y's, and y instead of x, so minus 4y minus 2x times x. Okay, so what I had? It sure is. Okay, so from here, we get either y equal to 0 or this other equation equal to 0. 108 minus 4x minus 2y equals to 0. From here, we get x equal to 0 or 108 minus 4y minus 2x equal to 0. We need these to simultaneously be 0. So we're going to get probably 4 different things. This and this, this and this, this and this, this and this, right? As long as one of these 2 things is true in each of them, we're going to get a critical point. And there's 4 different ways you can combine them. So let's say our critical points are going to be 0, 0. And then if x is 0, y can be 0, or 108 minus 0 minus 2y can be 0. So 108 minus 2y can be 0. Let's say y can be 54. So if x is 0, y can be 54. It seems probably too big, but that's okay. I feel like, no, that's fine. Yeah. Sorry, those numbers just seem kind of weird. Yes, that's fine. No, that's totally. I feel like I'm making a mistake here. Just let me check one thing real quick. What dumb thing am I doing? Yeah, sorry, I'm just looking at my notes here. Okay, okay. I see what I'm saying. So, okay, so let me just point out, the other number we're going to get is if y is 0, we can plug that in for here, we're going to get x equals 54. And yeah, although these are all critical points, none of them are going to be the right answer. Because, well, if x or y is 0, the volume of the box is going to be 0. So while you could look at these and determine that they're going to give you something that we don't want, we don't need to look at them, right? The question is just find the dimensions that maximize the volume. So the only thing that's left is to have this equation and this equation both be true. So I'm going to solve those both for either y or x. If I solve the first one for y, I get 108 minus 4x equal to positive 2y. So 54 minus 2x equal to y. If I solve this one, I'm actually going to get the same equation but for x, right? I'm going to get 108 minus 4y equal to 2x, so that x equals 154 minus 2y. So then, if we plug that in here, we can say that, okay, 54 minus 2 times 54 minus 2y equals y. So solving this, we get 54 minus 2 times 54 plus 4y equals y. Subtract 4y, negative 3y equals negative 54. So y equals 18. If y equals 18, x should also be 18. And it is, right? 54 minus 2 times 18 is 54 minus 36, which is 18. Okay, we should check to see it's a maximum, right? If we find, so let's see, if we find Vxx, let's see, Vx was 108x minus 4x squared. Sorry, Vx was 108y minus 4xy minus 2y squared. The partial of this with respect to x is going to be partial of 108y is 0, partial of negative 4xy is negative 4y. And the partial of negative 2y squared is 0. And then, gosh, I keep writing the wrong things. Sorry. I feel like, sorry, let me double check it. Something stupid here. No, that's right, okay. I just keep accidentally writing y instead of x. Sorry about that. And then VYY is going to be, let's see, so the partial, it should be negative 4x. And it is, right? If you take the derivative of this, 108x with respect to y is going to be 0, minus 4yx with respect to y is going to be negative 4x, and minus 2x squared with respect to y is going to be 0. And then finally, vxy, so the partial of this with respect to y is going to be 108 minus 4x, and then minus 2y, sorry, minus 4y. And so then finally, calculating the determinant of the Hessian, we're going to get vxx vy minus vxy squared, so that's going to be negative 4y times negative 4x minus that number squared, 108. Sorry, I'm kind of running out of room here. Minus 4x minus 4y squared. If I plug in my critical point, which is 18, 18, I'm going to get, let's see, I don't know. This is going to be some positive number. It's going to be 16 times 18 squared. And then minus, if we get 18 for y, 18 for x, 4 times 18 is, I don't know, let's just calculate. 108. 4 times 18 is 72, minus another 72 squared. So we have 16 times 18 squared minus 108 minus 144 is 36. And 16 times 18 squared is bigger than 36 squared. So this is positive, meaning we have a maximum or a minimum. And it's definitely a maximum because my second derivative, negative 4y, at the point is negative. So it's conjugated down. Okay. So back to answering the question real quickly here. The dimensions are going to be x equal to 18 inches, y equal to 18 inches, and z equal to, let's see, z is going to be, what do we got here? 108 minus 36 minus 36. So 108 minus 72 is 36. Great. So now what we're going to do is we're going to answer the question, but we're going to use LaGrange multipliers. So we're going to do one example using LaGrange multipliers, and then we will talk about explaining kind of why they work to some small degree. Yeah. So here's the idea. We want to maximize, still the same question, right? So we want to maximize the volume equal to x times y times z, subject to the constraint z plus 2x plus 2y equals 108. Okay, now here's the process that's going to work. Basically, you're trying to maximize some function. We usually call the thing we're trying to maximize, I usually call it f. I think that's the notation your book uses as well. Take a look. Yeah, they're usually using f and g. So I want to maximize lowercase f with the constraint of g. And your function g is usually set equal to 0, although it doesn't really matter where you put the constant. So you might say that g of x, y, z is z plus 2x plus 2y minus 108 equals to 0. It doesn't really matter where that 108 lives because we're going to be taking some partial derivatives. Okay, the easiest way I think to remember how to do this is to say the following. We're trying to solve this equation. The gradient of f is equal to lambda times the gradient of g. That's it. I mean, I know that's not it, but like, that's all you have to remember. If you remember what the gradient of f is and what the gradient of g is, they're both vectors, then this is what we're trying to solve. So again, we're trying to find x, y, and z that solve this equation. Maybe we'll find lambda. Maybe we won't. Nobody cares about lambda except that it helps us solve this situation. So lambda is helpful, but if you don't end up solving for it, nobody should actually care. So here's what we're going to write down. The gradient of f, I'm going to use column vectors because I find it easiest. So here's my gradient of f. Do I have enough room? Yeah, that's fine. So it's going to be, right, the partial of x, the partial of y, the partial of z. So the partial of x, or with respect to x, is yz. Partial with respect to y is xz. Partial with respect to z is xy. And it's going to equal lambda times the gradient of g, which is the partial of g with respect to x, y, and z. So partial with respect to x is going to be 2. Partial with respect to y is going to be 2. Partial with respect to z is going to be 1. So there's our equations. So then what we have to do is we have to essentially use these 3 equations to figure out what x, y, and z are. I should say these 3 equations. So let me back up 1 second. If you look at this, we have not enough equations. We have 3 equations, right? X, y, z equals lambda times 2, x equals lambda times 2, x, y equals lambda times 1. But we have 4 unknowns, x, y, z, and lambda. And you need as many equations as unknowns to solve a system, typically. There's our other equation. Z plus 2x plus 2y minus 108 equals 0. So we have a 4th equation. So basically what we're doing is we're going to use lambda to kind of help us relate x, y, and z. We're probably going to find both x and y in terms of z and then plug those into this equation to solve for z. All right. Do we have enough room? Not really. So the hard part about LaGrange multipliers is there's no one right way to kind of go about solving things. It's kind of a play around with it and see what happens. So we've got yz, xz, xy. Yz, xz, xy equal to lambda times 2, 2, 1. And then we also have the constraint equation, right, that we need to be true. We need z plus 2x plus 2y equal to 108. Or minus 108 equals 0. It doesn't really matter. So let's see. I've got yz times yz equal to 2 lambda, xz equal to 2 lambda, and xy equal to lambda. So I can set these equal to each other because they're equal to the same thing, and say that yz equals xz. Canceling the z's, I get y equal to x. Great. And then I can use these 2 equations and solve them both for lambda. So lambda equals xy. Lambda also equals xz divided by 2. Cancel the x's. Y equals z over 2. Or z equals 2y. So I can plug in 2y for z and x for y. So I get that this equation becomes 2y plus 2y plus 2y equal to 108. So 6y equals 108. Y is 108 divided by 6, which guess what? That's 18. Then z also, so then x is also 18. And z is 2 times y, so z is 2 times 18, which is 36. Done. So Lagrange multipliers are kind of cool. They're usually pretty easy. The only kind of, or I should say, one of the downsides to Lagrange multipliers is this doesn't specifically show it's actually a maximum, right? All we've really shown is that we found a place where this basically would, so in fact, let me actually, yeah. So this method allows us to find local maxes and mins, but it doesn't show us how to differentiate between them. So we kind of have to use other methodologies or explanations to kind of say, oh yeah, it's actually a maximum. Yeah. I'm just trying to see if they say anything about this in the book. Yeah, I don't think so. Not really. but we knew we were looking for a maximum, so let's just say it's a maximum. So now let's look at, so I'm going to do this next example, and then I'm going to show you these. Yeah, I'm going to show you the picture of the grant do, because grant do some really nice pictures that I think will help us kind of, or at least if you haven't seen this before, will help you kind of see why the heck this even works in the first place. But you should kind of notice, or maybe be aware, right? Basically, when you're setting gradients, if you're setting the gradient of f equal to a multiple of the gradient of g, what you're basically saying was, well, remember the gradient of f is the vector that's normal to the surface f. Gradient of g is the vector that's normal to the surface of g. And basically, we're saying that if you're setting gradient of f equal to lambda times the gradient of g, that the vectors that are normal to the surfaces have to be in the same direction. Right? They have to be multiples of each other. That's kind of what we're using here. But let's do a couple more examples. We'll do one more example. I'll talk about some explanation, and then I've got. Oh, there was a question that someone had that I should also do. So let's look at this one. This one's not too terrible to answer. Which point on the plane 2x plus 3y plus z equal to 6, is closest to the origin? Okay, so we're trying to minimize something. We're trying to minimize the distance between our point, our plane, and the origin, I should say. So we want to minimize the distance between the point, between the point and the, holy smokes, between the point on the plane and the origin. So let's say, right, in fact, I can even draw this plane. Right, our plane has a z-intercept of 6, an x-intercept of 3, and a y-intercept of 2. So our plane looks kind of like that. And there's some point on the plane, x, y, z, that is closest to the origin. So I want to find the point where the distance is minimized. So the distance between that point and the origin is the square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared. And we're not going to use the square root because we have learned already before that instead of minimizing the distance between a point and another point, it's always easier and nicer to minimize the distance squared. So we're trying to minimize this. And so that's our function f. And our constraint is that. Where we have to be on that plane. So that's our constraint. And we want to make this thing as small as possible. That's what we're trying to minimize. Okay. So again, I'm just going to write down that the gradient of f is equal to lambda times the gradient of g. It's not hard to remember that, right? Like there are other ways of doing this in the 16 series. They make it, they don't talk about gradients in the 16 series really. So there's like, you have to memorize 4 kind of equations. Because really what you're doing, if you look at this, is you're setting the partial with respect to x of f equal to lambda times the partial with respect to x of g. And then the partial for y equal to lambda times the partial, right? It's just you're setting all the partials equal to lambda times the other partials. But it's much, much easier, I think, to remember that as one equation. Oh yeah, the gradient of the thing you're trying to minimize equals lambda times the gradient of the thing you're trying. That is your constraint. It actually technically doesn't matter where you put your lambda, but it's standard to put your lambda on the thing that you're trying to, that's your constraint. Okay, so that's going to give me, let's see, gradient of f is going to be 2x, 2y, 2z. And the gradient of g is going to be 2, 3, 1. Okay, I feel like I'm missing something here. No, that's fine. What am I missing? So, I think what we have to do here, and it's always, yeah, so I think what we can do here is I think we can just actually solve, it's always a guessing game. Like, what do we do to solve this one? I think, so there's no way of relating x and y to each other. That might not be entirely true. Let's see what we get. So writing out the equations, I get 2x equal to 2 lambda. So x equals lambda. I get 2y equal to 3 lambda. So either y equals 3/2 lambda. Yeah, I think that's the way I want to go. And then 2z equals 1 lambda. So yeah, so z equals 1/2 lambda. And then I'm going to plug all those into my constraint, solve for lambda, and then solve for x, y, and z. Sometimes you solve for lambda. So if I plug those onto my constraint, what do I get? I get, let's see, 2x is going to be 2 lambda. 3y is going to be 3 times 3/2 lambda, so 9/2 lambda. And z is equal to 1/2 lambda, so we get 1/2 lambda equal to 6. So let's see, that's 10 halves, that's 5 plus 2 is 7, lambda equals 6. So lambda equals 6/7. So that means x is going to be 6/7. Y is going to be 3/2 times 6/7, which is 18/14. And z is going to be 1/2 of 6/7, which is 3/7. Let me make sure I didn't make a dumb mistake somewhere, just because I want to make sure I didn't. I did make a dumb mistake somewhere. Did I? No, I didn't. It didn't reduce it. Yeah. That reduces to 9/7. So yeah, that's what we get. So let me show you some of the stuff on this, just so I can say a few more words here. Let me share my screen for a moment. So if we look at this, well, first of all, notice that it's been drawn slightly differently, right? Instead of drawing the x-axis coming out at us and the y-axis going to the right, it's been rotated 90 degrees kind of away from us so that the x-axis is pointing to the right and the positive y-axis is pointing back. It just makes it kind of easier to see the plane, right? The plane I've drawn is kind of coming out at you, or the plane that's drawn there is kind of going back in a way a little bit. So here's what we got. We want to minimize this function, f equal to x squared plus y squared plus z squared, with this constraint that 2x plus 3y plus z equals 6. And here's the part that really is kind of takes a minute to wrap your head around. The trick is to think of both the function f and the function g as level curves or level surfaces, right? Notice that the function f equal to x squared plus y squared plus z squared equal to c has the form of a sphere, right? So again, we're thinking of these level spheres where the spheres get bigger and bigger and bigger and bigger and bigger, right? Depending on what your c value is. As the sphere gets bigger, the first point it will hit on the plane is the closest point, right? So at some point, right, you've got like really small spheres, like, you know, you've got like a sphere like, I wish I could draw this. You got like a sphere like this big, right? You've got smaller spheres, and then as the sphere is growing in size, the very first point on the plane it touches has to be the closest point, right? It's the point that's touching the plane that's on the sphere of the smallest radius. At that point, both the gradient of f, right, the vector that is normal to the sphere at that point, and the gradient of g, the vector that is normal to the plane, have to be in the same direction, right? They're both perpendicular to their level surfaces. So they have to be parallel, meaning they are multiples of each other. That's the whole idea, right? We're just saying to find where you have a minimum or a maximum, you have to find the place where the normal vectors to your level surfaces are in the same direction. It's kind of interesting. And then I will also point out, Grant did solve this a different way than I did. So he has the same equation, but then instead of doing what I did, where I solved each variable in terms of lambda, he isolated lambda, right? So he said, okay, lambda equals like, ooh, geez, sorry about that. Lambda equals x, lambda equals 2/3 y, lambda equals 2z. And then he used this equation to write x in terms of y, and he used this relationship to write z in terms of y. And then he plugged all that in back to the original equation, getting everything in terms of y, so you could solve for y. And then back for x and back for z. You still get the same results, but it's a different way of tackling it. most of the time you shouldn't have to solve for lambda, but sometimes it just feels like it's easier to. Okay. Let's look at, there was an example that someone sent me that I should go ahead and look at. This is problem 49 from section 14.7, which 14.7, interesting. So it's interesting. Well, maybe it's in my old textbook, section 14.7 is the extreme value section, but maybe 14.7 is the LaGrange multipliers in your textbook. Certainly the solutions that were sent along with it definitely were using LaGrange multipliers. Well, let's look at it. Ooh, interesting. Yeah. The nice thing about this is with some practice, it's actually a pretty straightforward methodology. So here's the question. Among all the points on the graph, so among all points on the graph of z equal to 10 minus x squared minus y squared that lie above the plane, x plus 2y plus 3z, zero, find the point that's furthest. Which point is furthest away? Okay, I'm going to try and draw this because I can kind of draw it, maybe. So here's my XYZ coordinate system. And I know that this thing here is the downward opening parabola, right? It hits the point 0, 0, 10, and then kind of does this. All right, looks like that. And then the plane x plus 2y plus 3z, so drawn in a different color. So x plus 2y plus 3z. Oh, I should point out, right? So this point right here is the square root of 10, right? 0, root 10, comma 0. And same deal here, root 10, 0. 0, 0, 10. And then my plane, x plus 2y plus 3z equal to 0. That's hard to draw. I thought it was going to be easier to draw x plus 2y plus 3z equal to 0. Goes to the origin, and then you've got like, I wanted to draw it, but now I'm like, maybe not. It's a plane, it goes to the origin. Let me think of, here's a couple points you could have. So if y was, say, 3, x could be, let's do, if y was 3, z could be -2, sure, over 1, 2, 3, which is almost root 10 and down 2. So there's a point on my plane, over and down. And then we can also have if x was 3, z could be -1. So again, here's 3, -1. And then if, I don't know, if z was 3, then x and y could both be -3. So maybe somewhere back there. Okay, so here's my plane. This is right. Okay, there's my plane. And the idea is what point on the surface above the plane, right? Because you could go, the surface keeps going down and it goes down forever. So any point below the plane would be like could be infinitely far away, right? You keep going down and down and down. So that's why we're saying where's that? Sorry. That's why we were saying among all points that lie above this plane, which one's the furthest away? Okay, it's a lot of setup for not a whole lot of solving, right? So again, so this one we do have to do one thing though. Before we can solve it, we need to write the thing that we are, so again, which is our constraint here? Oh. We're trying to find the point that's furthest away. That's a good question. In fact, let me take a look at this. Yeah, I feel like this is, yeah. I don't know if I like the way they've written this now that I'm reading this. We want the, so here's what the solution says. We want the point on z equal to 10 minus x squared minus y squared, where the tangent plane is parallel to the plane x plus 2y plus 3z, right? So again, same idea. We're looking for the point on the surface where the plane that's tangent is parallel to this plane here, or another way of saying it, both their normal vectors go in the same direction. Yeah, that'll be the point that's furthest away from the plane. Yes. Which seems a little bit funky. So we are going to say that, yeah. So, sorry, my brain is having a slightly hard time figuring out which thing is my constraint, which thing is the thing we're trying to maximize. I don't think it really actually matters. And maybe that's not really a thing here, right? Because we're trying to maximize the distance between these two things, but I don't actually want to write down that equation. What I want to do instead is just say, oh, no. Yes, this problem is a little bit different. So here's what they do. They say to find a normal vector to z equal to 10 minus x squared minus y squared, we're going to rewrite this as, how do they rewrite this to be consistent here? Yeah, they do it as x squared plus y squared plus z minus 10 equal to 0. And they call that w, but I'm going to call it f. I'm going to call it g, really. Yeah, sorry, I've gotten myself a little, I thought I worked for this problem before, just following the instructions, but I feel like it's not really, doesn't have the same sort of context that the other problems we've done have. But what we want is for that f, its gradient. So we want the gradient of f, we want that to be parallel to the gradient of this here. Right, where this is my, yeah, I feel like I'm hand waving something here, but maybe not. So I want the gradient of f, that's going to be 2x, 2y, z, sorry, 2x, 2y, 1, not z, equal to lambda times the gradient of g, which is 1, 2, 3. Well, that's easy enough to solve because literally lambda has to be 1/3. So we can say that 2x equals 1/3, 2y equals 2/3, and 1 equals 1. So we get x equal to 1/6, y equal to 1/3, and plugging back into this equation to solve for z, sorry, not this equation, we're not on this surface, right? We're on this surface. So plugging back into this equation to solve for z, we get z equal to 10 minus 1/36 minus 1/9. So that would be the point that is closest to this plane on this surface. Yeah. I kind of feel like I should do it a different way. Let me ask, how many of you guys care? Do you feel good with this, or would anyone like me to talk more about this problem? Okay, sounding like a big old, you guys are like, we can do whatever. Okay, that's fine. Yeah, I might have to think about this one later. Yeah. Okay. Sure, I can let it go. Yeah. I guess. Yeah, no, I guess that's really the only way to approach it. Because you can't, so I guess the thing I was thinking that could work, but I don't think actually does work, is you'd be trying to find the point on the surface that's furthest away from the plane. So you'd be trying to maximize the distance between the point on the surface and the plane. But the problem is we don't really know either point, right? It can be any point on the plane and it can be any point on the surface. Unlike the previous sphere example where we knew that we were trying to find the maximum distance from the origin. So I don't think that idea actually works. I think you have to tackle this one this way. That's kind of interesting. All right. Sure. Let's do one or two more LaGrange problems, and then if we have time, we can do some problems where you're talking about maximizing, minimizing something over a specific region. Okay, let's look at this one. Excuse me. The temperature on an ellipsoid, which is given by the equation x squared plus 2y squared plus 3z squared equal to 30, is given by t equal to 2x minus y minus 3z. And the question is, what are the hottest and coldest points on the ellipsoid? Or in other words, maximize / minimize t subject to the constraint draw on the ellipsoid. You always want all your variables on one side. Both of these have this, right? We're trying to maximize this, given this equals 30, or this minus 30 equals 0. Either way, as long as your constant isn't on, it doesn't. Oh God, words. Doesn't matter what side your constant's on. That's what I'm trying to say. So we're trying to say, I'm going to say that this is the thing this is my constraint, so that's my G. This is the thing I'm trying to maximize. So this is my F. So I've got the gradient of F equal to lambda times the gradient of G. So it's going to be, let's see, the gradient of F is 2, -1, -3. And the lambda times the gradient of G is going to be, let's see, 2x, 4y, 6z. Seems not too awful. So let's try and do the thing where we don't actually solve for lambda. So here's what I've got. I've got 2 equal to 2x lambda, -1 equal to 4y lambda, and -3 equal to 6z. And this pen feels like it is going. So solving each thing for lambda, I get lambda equal to 1 over x, lambda equal to -1 over 4y, and lambda equal to -1 over 2z. So setting these two equal to each other, I get 1 over x equals -1 over 4y, or x equals -4y. Setting these two equal to each other, I get -1 over 4y equals -1 over 2z, reciprocal of both sides, and get rid of the negative signs. 4y equals 2z, so z equals 2y. So we've got everything in terms of y. Let's plug those back into our constraint. So plugging those into our constraint, I've got -4y quantity squared, so I'm going to get 16y squared plus 2y squared plus 3 times z is 2y, so 3 times 4y squared is 12y squared equals 30. So 16 plus 12 plus 2, someone came up with nice numbers, that's equal to 30. So I get 30y squared equals 30. So y is plus or minus 1. And then my x and z are going to be specifically, let's see if y is plus or minus 1. X is, whoops, let's not write that right there. x is going to be the opposite sign. So x is going to be minus plus 4, because x is negative 4y. And z is going to be 2y, so z is going to be plus or minus 2. So the hottest and coldest points are, which I literally just erased the equation I wanted. Oh well. My temperature, if you recall, was given by 2x minus 5 minus 3z. So my hottest and coldest points are going to be at 1, negative 4, 2, and at negative 1, 4, negative 2. So, which kind of makes sense if you think about it, because this ellipse is kind of, it's centered at the origin, meaning it's kind of has symmetry about the origin. So if your hottest point is kind of that way, then the coldest point should be in the opposite direction of it, which is what is happening here. Which one's the hottest, which one's the coldest? Let's see. If I do T of this one, being really easy, okay. Fine. So at this point, the temperature is equal to 2 plus 4 minus 6, so 0 degrees. Fun times. I feel like I made a mistake there. I did make a mistake. The mistake I made was I wrote my x, y, and z out of order, but I accidentally put it in order, right? Y is 1, x is negative 4. Let's rewrite that. Easy to make dumb mistakes like that if you're not paying attention. So I've got the point negative 4, 1, 2, and positive 4, negative 1, negative 2. So there, my temperature is going to be, let's see, negative 8, minus 1, minus 6 is negative 15. And here it's going to be positive 8 plus 1 plus 6, which is 15. So my coldest temperature is negative 15 degrees, my hottest temperature is positive 15 degrees. And the hottest point is this one, the coldest point is this one. All right. Let's look at another example. So sometimes a LaGrange Multipliers question can have two constraints. So let's look at this example and kind of see how it's different. So I want to find the point on the line of intersection of the two planes y plus 2z equal to 12 and x plus y equal to 6. So I'm going to find the point on the intersection of those two planes, which we can totally find the intersection of those planes, but we don't need to. But we could write the equation on that line if we wanted to. We want to find the point that is closest to the origin. So here's what we're trying to do. We are trying to minimize the distance, but really we use the distance squared. So minimize the distance squared with the constraint, with these constraints. And so I'm going to call this F, and we usually call these G1 and G2. So here's how it's going to be different. Instead of doing the gradient of F is equal to lambda times the gradient of G, it's going to be the gradient of F equal to lambda times the gradient of G1 plus mu times the gradient of G2. And then we're going to solve this system. Let's see what we get. So the gradient of F is, no surprise, it's 2x, 2y, 2z. The gradient of G1 is 1 plus 2, oh, sorry, 0, 1, 2. And the gradient of G2 is 1, 1, 0. Okay, so here's our equations. 2x equals mu. 2y equals lambda plus mu. And 2z equals 2 lambda. Okay. So I would say, right, lambda equals z. Yeah, this always gets a little like, how do we solve this? Let's see. So I guess we can plug those in here and say that we know that 2y equals mu, which is, sorry, lambda, so z plus mu, which is 2x. Does that help? Maybe. We probably need another equation. Let's see, what else have we got here? Oh, yeah, I see. Okay. So now we've got 3 equations and 3 unknowns. Yeah, that's kind of funky. So, sorry, I hope you don't mind me erasing that. And we can solve the system of equations here. So I've got y plus 2z equals 12. I've got x plus y, and we're doing this, yeah, x plus y equal to 6. And rewriting this one, I'm going to write it as 2x minus 2y plus z 0. And I'm kind of writing this in a suggestive way. I'm kind of writing it like a matrix. Not that you have to use matrix stuff to do this, but you could if you knew how to do that kind of thing. So probably the easiest way to solve this is to solve this for y. Sure. So let's say y equals 12 minus 2z. Plug that in here and here. Then you've got x plus 12 minus 2z equal to 6. Plugging it in here, you've got 2x minus 2 times 12 minus 2z minus 2z equal to 6. Excuse me. Sorry, did I just, no, that's sorry, I made a mistake there. Sorry, I'm plugging it into this equation. It's 2x minus 2 times 12 minus 2z plus z equal to 0. And then you can solve each of these for the same variable and set them equal to each other. So I think I'm going to erase here. So let's see, we're going to have x equal to 2z minus 6. And here we're going to have 2x minus 24 plus 4z plus z equals 0. So I can plug in this here and get 2 times, let's just multiply it out. 2 times this is going to be 4z minus 12 minus 24 plus 4z plus z equals 0. So 9z minus 36 equals 0. So z equals 4. And then z equals 4. We get x equal to 8 minus 2. Sorry, 8 minus 6, which is 2. And then we get y equal to 12 minus 2z, so 12 minus 8 is 4. Kind of an algebraic pain, but not too terrible. Yeah. So the closest point on, the closest point on the intersection of these two planes to the origin is the point 2, 4, 4. All right. So I'm going to give you guys one to work on because I need to use the restroom. Because apparently I'm just the oldest man in the world now. I have to go to the bathroom all the time. I know you don't care. It's really not important, but it's my life. Okay, so we give you guys this problem. Another one where you have 2 constraints. Oh, 2 constraints? No, not 2 constraints. Well, this one's kind of tricky. No, you guys can do this one. So I want you to do this one. So use LaGrange multipliers to find, so I want you to find the max or min, the extrema of this function, f of x, y equal to 3x squared plus y, subject to the constraint x squared plus y squared equal to 1. So that's going to be your g. That's what we got. This one only has x and y. There is no z. So go ahead and set delta f equal to lambda, or I should say, right, the gradient of f equal to lambda times the gradient of g, and work on solving that. I'll be right back. Okay, sorry about that. Let's go ahead and see what we got here. So, oh my God, there's totally another way you can do this one as well, which is kind of interesting. That's fine. So we can do this by saying partial here, sorry, gradient, not partial, 6x1 equal to lambda times gradient here, 2x, 2y. Seems good. So what am I going to see here? See, it's really bright up there. So let's see, I've got 6x equals 2 lambda x. Then I have 1 equal to lambda times 2y. And I can solve for lambda. Lambda equals 1 over 2y. I can solve for lambda here. Lambda equals 3. Does that seem right? So we have to be a little extra careful here, right? So I divided both sides by 2x. That's not the only solution. I can have lambda equal to 3, but it would also be correct to say that x could be 0. Both of those are true. So if lambda equals 3, then we're going to get, let's see, then I should just solve this for y. Y equals 1 over 2 lambda. So that means if lambda equals 3, then you get y equal to 1/6. And then using your constraint to solve for x, you get x squared plus 1 over 36 equal to 1. So x equal to plus or minus the square root of 35 over 36. Okay, that's one possibility. Or actually, that's two possibilities. And then the other possibility is, well, if x is 0, then y can be plus or minus 1. So there's actually 4 points to check. So which one's going to have the biggest value, which is going to have the least value? Well, let's find out. Sure, I can erase this. So f of 0, 1 is going to be 1. F of 0, negative 1 is going to be negative 1. Using these points here, f of, it shouldn't matter if x is positive or negative because this will still square it out. So f of plus or minus the square root of 35, 36, comma 1/6 is going to give us 3 times 35 over 36 plus 1/6, which is, let's see, that cancels there. You get 35/12 plus 2/12. That's going to be 37/12. So there's the smallest thing. There's the biggest thing. So this one has a maximum at both positive and negative root 35 over 36, 1/6, and it has a minimum at 0, negative 1. Interesting. Yeah, time-wise. Okay. I think that pretty much is enough about LaGrange multipliers, unless you guys really want to see a couple more. But there's another type of question that I kind of, I don't want to say skipped over, but we just didn't do yet. So let's look at a couple examples which I think are worthwhile. Yeah. So let's see, how do we phrase this? Let me see. I feel like there's a better way of saying what I want to say here. Let me look for 1 second. Sorry, it's one thing I want to see. Okay, that's fine. Yeah. All right. So I want to find the absolute maximum and minimum values of, I should say, I want to find the, absolute maximum minimum of the function, our good old function, 9 minus x squared minus y squared. And now I want to be on the region, that's, let's see, how do I want to describe this region? On the closed boundary region, that is a square with corners -3, -3, 0, sorry, not 0, 3, 3, 3, -3, and -3. So here's the idea. Want to give you the idea first, or do I want to give you? Let me see. Let me show you first. So we know what this function looks like. We know that 9 minus x squared minus y squared. Well, I've drawn it like this before. And this point, right, is 3, 0, 0, 3, 0. This point is 3, 0, 0, etc. Now the problem is, I want to look at the maximum and minimum values of this function over this region that's a square. meaning I have to let this function go down further, right? This part, right? This function, although I've drawn it this way, it doesn't end there, right? It goes down forever and ever and ever. So I have to kind of see like, okay, if I let this go further, what happens? Well, what happens is, in fact, I'm just going to draw it over here. What happens is, yeah, can I draw this? Maybe. Maybe not. Sure. So we still get the same sort of parabola thing happening this way and this way, except we are, yeah. So we're still ending there and there. We're still doing this. We're still doing that. We're still getting this kind of circular shape. But then what's happening is, right, in this kind of corner over here, and over here, and over here, and over here, it still gets to keep going downwards because I haven't exhausted my region. So what's going to happen is it's going to keep going like that. And the same kind of deal over here, right? It's going to keep going. I used to be able to draw this better. Wow, that's terrible. Okay. So let me just draw the thing the way I know how to do it. It kind of looks like this. And so it kind of looks like that. And then like at this, and I haven't like done super excellent job of this, but like right here in this level plane is where we have like that circle. So the idea is we want to find the absolute max, absolute min. Well, it should be pretty clear from the picture. There's the absolute maximum. But it looks like there's some possible absolute minima. So how do we do this? I know I just spent drawing. So we draw the region. Here is my square with points. As the corners. And also we know what the, so it's kind of like how in 21A, sorry, stuff, when you wanted to maximize and minimize something on a closed interval. And in addition to testing the critical points, we would also test the boundary points, the left and the right endpoints. Well, it's the same idea here. There's just more boundaries to deal with. So we're going to test every corner. And we're also going to test for relative extrema on each boundary. So y equal to 3, x equal to 3, y equal to -3, x equal to -3. All right, so let's find the critical points. So we're just going to do the usual thing, setting each partial equal to 0. So fx is -2x equal to 0. Fy is -2y equal to 0. We get the point 0, 0. No big deal. Okay, but then we're also going to look on each boundary. So if I set y equal to 3, then my function is, I should really write f of x comma 3 is equal to 9 minus x squared minus 9, so it's just -x squared. The partial with respect to x is -2x. The partial with respect to y is just 0. So if I set this equal to 0, I get x equal to 0. So 0, 3 is another point I have to check. So I'm going to make my list over here. So 0, 0, 0, 3. So what we're kind of seeing with this point 0, 3 is, I don't know if it's an absolute maximum or minimum, but I do know that it's essentially bigger than or smaller than everything that's around it. It's a local max or min for sure. And if you look back at the picture I had drawn, you're essentially saying we're looking at, this point right here. Yeah, it's bigger than the stuff around it, but it might not be the biggest thing overall. It's not, but that's okay. And so in a similar way, we're going to find that each of these points in the middle happen to be a critical point, or an endpoint, I guess more is the better way to say it, right? If you look at x equal to, or you're going to get the same thing for y equal to -3, right? If y equals -3, you're going to have f of x comma -3 is also negative x squared, and then the derivative will be equal to -2x, which gives you x equal to 0, so you get 0, -3, and then you can do the same thing for x equal to ±3. You're going to get your function of ±3 comma y equal to 9 minus 9 minus y squared, and then the partial with respect to y is going to equal just -2y, which is going to be give you y equal to 0. So these are our 1, 2, 3, 4, 5, 6, 7, 8, 9 critical points we have to check. And then we just plug them all into the original function. So f of 0, 0 is going to be 9. Right, that's the point right there. I just labeled it though. And then f of 0, 3 is going to be 9 minus 9 minus 0, so it's going to be 0. And f of 0, -3 is also going to be 0. F of 3, 0 is going to be 0. F of -3, 0 is going to be 0. But then we also check the corners. F of 3, 3 is going to be 9 minus 9 minus 9, which is -9. And in fact, all of the corners are going to be -9. So you're going to get an absolute maximum at 0, 0 with a y value of 9, and 4 absolute minima at the corners 3, 3, -3, 3, -3, -3, and 3, -3, and each of them will have a minimum value of z equal to -9.